to that, okay? What happened last time, right, when we did the derivation before for Cartesian coordinates, this thing went to 0, right? How the coordinate system changed with respect to time. When it was a Cartesian coordinate system, it was off to the side and it wasn't changing at all. And so we took the derivative of like di dt, that just went to 0. In this case, though, it doesn't go to 0, right? My coordinate system is changing with respect to time, right? And so now I can't just make that term go to 0. That's where I use what I wrote on the previous page, right? How does that unit vector change with respect to time? Right? dE hat dt, right? That's going to be d theta dt in the normal direction. Theta dot in the en direction is equal to omega in the en direction. Just writing the same thing. This is from the previous page. Okay. Everybody see that, right? So we took the derivative, we did the product rule, applied the product rule to it, then it got bigger. Then we take the derivative of the direction, and that's just going to be omega in the normal direction, right? Normal to the ET direction, which happens to be En in our coordinate system right here, right? I don't know why I give so much space sometimes. There it is. That's what my acceleration is in this coordinate system, right? And this might be a little bit more familiar to you now. We're getting close to being familiar to you, okay? So this is our acceleration term, right? We have two components. We have an acceleration term in the ET direction, right? That's our change in, this part right here. That's our change in speed. Right? And this acceleration term right here, this here is change in direction. Now you're starting to see it, baby. Right? You've seen this before in physics, right? When something's accelerating, right? When something's accelerating, there could be two things that happen. One, you could be changing your speed, and two, you could be changing your direction. Because velocity is a vector; it has a position and a direction. If either one of those things change, what's nice about this coordinate system is it kind of separates those two things out, right? We have the change in speed component separated from the change in direction. Okay. Again, in this form, you may not recognize these terms, right? So we're gonna talk about some different forms of this theta dot. There's a couple different ways to write it. Other forms of theta dot. Okay. So if we're talking about how something changes its position, we'll call that change of position ds. This is our magnitude, or that's our radius. So this is something that's going from, here to here, right? And we have a radius rho, and we're changing a d theta. Right? I'm changing the angle in between them. Okay, if I wanted to calculate, these are all related to each other. If I wanted to calculate ds, let's say ds is equal to rho times d theta. Okay. This is just same thing you use for calculating the circumference of a circle, right? The circumference of a circle, you take the radius and you multiply it by an angle, right? And it'll tell you the distance over which it's traveled, right? So that's why we get 2 pi is the angle, r is the radius, and it tells you the whole circumference of the circle by doing that. So that's all we've done here. We just said, hey, my ds, right? My change in position along the length is just going to be this rho times d theta, okay? Pretty simple stuff there. Okay, so then we'll come back up to velocity here. Velocity is equal to ds dt. We can substitute in what we just found for ds. That's just going to be rho d theta dt, which is going to be rho times theta dot. It's going to be equal to rho times omega. that velocity, we can rewrite velocity as being rho times omega or rho times theta dot. Okay? And so I'm going to summarize that. My omega could be equal to theta dot. It can also be v over rho. Oh, I already wrote that. That's right here. Good for me. Good for me, Mike Berry, for several years ago. Okay, so what does that mean? Well, we can do some substitutions down below. So just an overall summary, what's happening, right? My velocity is just going to be ds dt in the et direction, always in the et direction. Velocity is pretty boring in this coordinate system. Okay, accelerations. My accelerations, like I mentioned before, have two components. Right? It has a component here associated with change in speed, an acceleration component here, which is change in direction. This AT is just going to be my change in speed. It could be either this, it'll just be v dot, right? But then the AN term here, this AN term can be any one of these, right? Some better than others, right? It could be v squared over rho, or it could be rho omega squared. You'll use one of those two. You won't use these other ones, right? You'll see when we do a problem, sometimes you know what the velocity is, right? And sometimes you know what omega is, right? And you can always relate the two, right? Velocity is just going to be rho times omega. But usually you'll go through the whole problem, you'll know what velocity is, or you go through the whole problem, you know what omega is, and you're just going to want to keep it. You want to keep it like this, right? Either you do it rho omega squared or v squared over rho, right? And those accelerations will be in the en direction. What are these accelerations? Everybody recognize those accelerations? V squared over rho or rho omega squared? You remember physics, right? You did physics. You did this stuff in physics, right? You had a bucket filled with water and you're whipping it around a circle and stuff stays in the bucket, doesn't come out of there. What was this? What was the centripetal accelerations, right? That's what these are right here. These are the centripetal accelerations, right? And you're probably used to seeing as like r omega squared or v squared over r, something like that. But there they are, right? They exist here. Okay. Special case, a circle, right? So if something's traveling around a circle, and actually I think almost all of the problems that we do with these normal tangent coordinate system fall into this category where things are traveling in circles, okay? That's something where we know that's the path. I know the path of a circle, okay? In this coordinate system, it takes some getting used to doing these different coordinate systems because they're a little strange, right? In this coordinate system where my particle's at over here, this is my ET direction, right? That's if it's traveling this way, right? I got an omega this way. And then my EN direction would be this direction. Okay, so traveling around. When it's over here, though, just at a different time stamp, this is why it gets a little confusing. My EN is this direction, and my ET is this direction. Okay, and it takes a little getting used to. It's just like, well, when something's traveling around in a circle, and we're going to solve for my velocity and my accelerations, and those velocities and accelerations, sometimes those velocities and accelerations are going to be here and here that I'm talking about. Other times it's going to be here and here. Or if it's down here, my velocities and accelerations will be associated with that coordinate system. You're like, well, that gets a little confusing. And it does, right? But when we're trying to figure out like the force required for something to stay in the middle, that's where we're ultimately going to build up to. It's like, all right, well, what kind of force is required to keep this thing rotating around in the circle? I don't really care, the tension in that cable, this bucket on, the bucket filled with water. I don't really care that, sometimes that force is this way or this way or this way or this way. I just care that it's there, right? And that it's pushing back towards the center of this circle that's traveling around, right? Where things get a little hairy, and we'll talk about this a little bit later, is if I'm trying to say, okay, if I've got two particles, right? And I've got this particle and I want to say, are they close to each other or do they hit each other or something like that? Then I have to start worrying about it, right? Now I have to start going, well, both of them are going to have their own ET in the EN direction, and they're going to be at different locations at different times. If I'm trying to relate the two, then things get a little weird. And we'll do an example with that later. And basically when that happens, the only way to do that is to go back to a common coordinate system. You have to take this coordinate system and then go back into the normal or into Cartesian coordinates and then start comparing things via Cartesian coordinates. Okay. But anyway, so I'm getting ahead of myself, right? So we have this ET in the EN direction. This thing's rotating around. Okay. So there's a circle. In this circle, rho is equal to r. My instantaneous center of curvature is actually the constant center of curvature, which is equal to r. My rho is equal to r. The other thing that we're going to apply here is that this is back to the circumference of a circle here, right? If I want the distance s along a path, I could just take the radius and I multiply it by the theta that's changing, right? That's just the arc length. That's just an arc length equation, right? So the s is just going to be r times theta. So when we come down to my velocity, that's going to be equal to ds dt, which is going to be equal to dr theta. I'm going to substitute in what ds is. This is r times theta dt. R is constant, so that can come out of that. And so that'll just be r omega in the ET direction. So my velocity is just going to be r times omega in the ET direction. I can calculate its velocity based off the radius and the omega. Right? So that's my velocity. And then we come down to AT is going to be equal to dv dt, which is equal to dr omega. R is constant again, so that can come out. And that'll just be r omega dot, which is equal to r alpha in the ET direction. And then when we come down to, last one we have to do is EAN, right? That's the change in speed, what AT is. Our change in direction, we're just going to use what we did before. That's just going to be either V squared over R, or it's going to be R omega squared. Either one of those, just depending on what you're doing with it. If I know my velocities, our example that we're going to do in a little bit, we know velocities. Sometimes you know omegas. This thing simplifies down. And this is what we're going to use here. These versions of the equation.
Does A have to bar over it?
Yeah, and no, because it's going to be in the, well, yeah, I'm not done yet. Hold on. Let me finish. Probably the best thing to do would be because the bar is going to be on the direction here. I got a little loose. I got a little nuts here with my. This probably should be a. What I should do. I should get rid of this one. That's what I should do. I'll fix it. I think technically all of them are right now, right? Because the direction is, we usually don't talk about AN and AT being vectors themselves. The overall A is a vector, and then the AN is just this magnitude out, this magnitude out front, either R omega squared or B squared over R. And then R alpha is the AT, and the direction is in the ET direction. Go.
Those V's in the equations, they're speed, right?
They're no, these are yeah, those will be speeds. Okay. Yeah, because you won't be the vector, it'll be the speed of it. Yep, absolutely. The magnitude of the velocity. Okay. All right, so we talked before, sometimes you're going to want to convert back to Cartesian. The reason you would do this is if you're trying to compare two different objects that are both like traveling around in a circle, for instance, right? So there might be a case that happens, right? And so what we do, right, what you do You just use this little diagram right here, right? So this thing, basically you have something that's traveling along a path. It has a coordinate system. This is ET hat, and then something perpendicular to that would be EN hat. Right? And then what you do is you come in and you stick our Cartesian coordinate system based right at that location. You come and stick that, the I and J, put it right there. Okay? And then literally it's just trigonometry at this point. Right? We can break the ET direction up and say, oh, it's got a little bit this way. It's got a little bit this way. Right? Same thing with our EN. It's got a little bit this way. It's got a little bit this way. Right? And we can break it up. Each one, the ET, we can break it up into its X and Y components, and EN we can break up into its X and Y components as well. And that's how you do this. Right? I'm not going to get into too much detail. I'll just give you what it ends up being. So ET hat is equal to cosine theta in the I direction plus sine theta in the J direction. And EN hat is equal to negative sine theta in the I direction plus cosine theta in the J direction. Right. So that's how you would convert between the two, right? And that's all literally just based off of this little diagram you see down here, right? And so the way this works, right, is that when you go through and you figure out what your acceleration and velocity are in the ET and the EN direction, you just come in and every place that you see ET, you substitute in cosine theta in the I direction plus sine theta in the J, and everywhere you see EN, you substitute in negative sine theta in the I plus cosine theta in the J, right? And we'll do an example probably next time that kind of demonstrates that, okay? Just in case, something like that might turn up. Okay. Let's do an example so we can kind of dive in here a little bit. Okay. Cars traveling along a circular path, R equals 300 meters. Speed is increasing uniformly from 15 to 27 meters per second in 3 seconds. It wants to find the magnitude of the acceleration at the when velocity is 20 meters per second. Okay, so we're after acceleration, so I'm just going to write down what acceleration is. Right, an acceleration vector is just going to be AT in the ET direction plus AN in the EN direction. AT is our change in speed, right? And this is going to be a constant acceleration, and they tell us what it's doing. It's going from 15 to 27 in 3 seconds. So I can figure out the change in speed. That's going to be 27 minus 15, that's the change in speed. And it said it took 3 seconds. 27 minus 15 divided by 3, that equals 4 meters per second squared. So that is what my AT is. Right, so that's just part of it. Right? Now I need to figure out what my AN component is. This is a very simple example, by the way. AN is going to be equal to either R omega squared, right, or V squared over R, right? They're all related to each other. Right? In this particular case, the V squared over R is going to be more useful to us, right? I could turn everything into omegas and then do R omega squared, but they tell us that the velocity is going to be at 20 meters per second. That's what we're solving this for, is when the velocity is 20 meters per second. So V squared over R is what we're going to use, right? So this is just going to be equal to 20 squared divided by the radius in this case is 300, right? 300. That'll be 1.33 meters per second squared.
Where did you get 20 from?
The problem statement, right here. Find magnitude of acceleration at velocity equal to 20 meters per second. Okay? All right. And this obviously makes an assumption that it's a constant acceleration, right? They don't tell us that it's constant acceleration, but we make that assumption when we do this. When we do 27 minus 15 divided by 3, assumes it's constant. All right? And then our vector ends up being, right? Now we get write it out as a vector. My acceleration vector would be 4 in the ET direction plus 1.33 in the EN direction. Okay, this is meters per second squared. Okay, but what the problem statement actually asks for is the magnitude of acceleration. How do we get the magnitude of a vector? Square root of the sum of the squares, right? That gives the magnitude. You often see magnitudes written mathematically like this. The bars on the side, and that'd be the square root of 4 squared plus 1.33 squared. 4.22 meters per second squared. There's my answer. When they talk magnitudes, that's what they're after. They're after the square root of the sum of the squares. So sometimes they'll ask for that. Right? And so then that tells you that it's overall acceleration, which will incorporate the change in direction and the change in speed along the length. Cool. Trying to do that particular problem with Cartesian coordinates, that's a pain in the butt, right? Hopefully you kind of see that. Like you wouldn't want to use Cartesian coordinates when something's traveling around a circle. Things get too complicated. It's hard to pull out. It's hard to figure out. What's the change in direction part versus the other part. Could you do it in Cartesian? Yes, right? You could. You would just have to know that there's this centripetal change in direction thing, and you have to do a bunch of sines and cosines and stuff like that to figure out, what it relates to in the I and the j direction. So this is maybe a good example of why you would use this. All right. This one I'm not going to do today. This one is kind of like the one before. This one starts out with the position as a function of time, and then you take the first derivative of it, and it'll tell us what omega is. Then you take the second derivative of that equation, it'll tell you what alpha is, and then you can go from there. Okay, so this is one of those types of problems where you start out with position and work your way the other direction. I don't want to do that one though. Let's do this one. Okay, given an electric car, I don't know why electric car, but the car starts at point A. Right? These came out of a book or your book. So this starts at point A and it travels around this corner to point B. Okay, so it's kind of a two-part problem because we're going to have a straight direction here and then going around the corner here. You can actually put them all together, but there's two different paths that this thing is on. Okay, the equation for the change in speed, right? AT is the change in speed, is 1 plus 0.2 t, and that's meters per second. Okay. I think yours might look a little bit different here, but find velocity and acceleration at point B. So they want me to find the velocity and acceleration at this point over here. Right? So this thing's traveling along the path, and then it goes around the corner and ends up over there. Okay, so just kind of lay out what we're going to try to do, right? We need to figure out what my velocity is. My velocity is going to be v in the ET direction, which is going to be equal to ds dt in the ET direction. That's my velocity is, right? They tell me what my acceleration is, right? What kind of problem is this when they give me acceleration like this? What kind of acceleration problem is that? It's a function of time. It's a function of time. So this is these ones are pretty straightforward. Acceleration function of time. So we're gonna figure out what my position is and my velocity is by doing some integration along the way, okay? And then my acceleration here, just to kind of lay out what we're doing, this would be AT in the ET direction plus AN in the EN direction is equal to V dot in the ET direction plus, we're going to do V squared over R in the EN direction for this, because I'm going to figure out what the velocity is at this point B. Right? If I know what that velocity is, instead of figuring out what omega is, I'm just going to use that velocity for determining what my normal component is. Okay? So now we got to come back. We got to find velocity first, right? I know what my AT is. This is just AT. They tell me what AT is. Right? There it is. There's what AT is. So this part's easy to find here, but I need to know velocity. I need to know how fast it's going when it gets to this point so I can figure out its centripetal acceleration. Also, the problem statement asks for it. If I'm after this velocity here, I need to know what the velocity is at point B, okay? So let's do that. Right? AT is a function of time, and it's going to be 1 plus 0.2 t. And that's going to be equal to dv dt, right? Acceleration is the time rate of change of that, so it's dv dt. That's what my acceleration is. I put the t's all on one side, right? 1 plus 0.2 t dt is equal to dv. Integrate this side, integrate this side. This is going from 0 to t. This is going from 0 to v. Okay, now I'm going to carry out this integration on both sides. Carry out the integration on both sides. This is going to be equal to t plus 0.1 t squared. Right, so that's just the integral of this. And that'll be equal to v. All right, so if I carry out this side, all right, that's just going to be v minus 0, and so we'll just have v. So there's my velocity as a function of time. Right? That's what I talk about. You just carry out the integral, and then carry out the integral on the other side, and then solve for what you're after, right? And I'm going to solve for v right here. When I carry that out, this is what I get. Right, so this right here is the velocity as a function of time. Okay? And that's going to be, so there we go. I got velocity as a function of time. What I don't know is how long does it take to go from here to here, right? I don't know that yet. I don't know what the velocity, I don't know how much time that is. So I have to figure out distance. I got to keep going with this. I got to look at distance. V is equal to ds dt. Right? And so t plus 0.1 t squared is equal to ds dt. Right? Put all the t's on one side. T plus 0.1 t squared dt is equal to ds. Right? Just going through our same method for solving these things. Right? This thing's going from, I'm going to integrate this. This one's going from 0 to t again. I don't know the time. And this one's going from 0 to SB. That's the total distance. SB is this distance right here. All the way around that corner, right? Because it's that acceleration, even though it's changing directions, but in this point right here, that acceleration, it doesn't say that it just means this acceleration is tangent path. So it's accelerating like this around that whole corner. It's this equation, this part of the problem doesn't care that it's going around the corner at this point. It's just how far does it actually travel in that amount of time. It's accelerating over that whole distance, right? And that I do know. I can figure out what that is, right? That's going to be 200, right? It'll be this track distance right here plus this track distance right here, which is going to be r times this angle here, that 90 degrees or that pi over 4, okay? Or pi over 2 rather. Okay? So SB, you can write down that SB. Actually, let's simplify this. This is going to be, when I carry out that integral right here, this is going to be t squared over 2 plus 0.1 t cubed over 3, and that's equal to SB. SB is equal to 200 plus the angle, pi over 2, multiplied by the radius, in this case is 50. That should be 278.5. Okay, that's what my SB is. I take that SB and I put it in right there. Okay. And then when I solve for that, right, I could solve for that. What would I do? I plug that thing in my calculator, right? It's a cubic, right? So the quadratic equation is going to do you no good there. Do you know how to solve a cubic by hand? Is there a way? I don't know. Long forgot. I long forgot with my calculator, right? So you use your calculator to solve for this, right? You set 278.5 equal to t squared over 2 plus 0.1 t cubed over 3, and then say, what is the time? And the time that pops out right here, t is equal to 16.33 seconds. Okay, so it takes 16.33 seconds for this car to go from here to here, to B. Okay, so now I need the velocity at that location, right? Because then I can plug it into my statement up above. So now I take the velocity is equal to, t is equal to 16.33. So I plug it into this equation up above, this equation right here, right? I plug it into that equation up there, and my answer that I get here is 43 meters per second. Okay, and so my velocity equation, the first part of the problem here, the velocity vector rather, is 43 in the ET direction, meters per second. Okay. And so in this coordinate system, right, the velocity at point B is going that direction right there. It's going up. It's in the, because that's where ET is pointed when we get around that corner. Okay, so now we can come back. The last part of it is figuring out the acceleration, and we'll do that really quick. It's just right here, right? So I come back to AT. I figure out what AT at t equal to 16.33 seconds. Right? And you just plug it into that equation. That's 4.27 meters per second squared, right? AT was given to us. We know what that is as a function of time. So you plug in the 16.33 into that equation, you get 4.27. And then my AN, almost there, AN is equal to V squared over R. And so this would be 43 squared over 50, which is 36.98 meters per second squared. And my overall A then is 4.27 in the ET direction plus 36.98 in the EN direction. Whew. What a journey. Okay. You can see that there's a lot of acceleration back towards the middle. There has to be, right? There has to be that change of direction. There has to be acceleration back to the middle. If there's not, right, you're not going to be on the path. You're going to fly off on a tangent if you're not accelerating back towards the middle. So this is, right, trying to do this type of problem with Cartesian, you couldn't do it, right? So we're going to do so we're going to do this one.
You have to put your unit after that.
What's that?
You have to put your unit after that as well.
Oh yeah. That wasn't done yet. I was just gonna say, what's missing?
Does this one want the magnitude?
What's that?
Does this one want the magnitude or?
Oh, I don't know if it asked for magnitude or not. It didn't say, so I would just say leave it in vector form at that point. Okay. So what we'll do next time is we'll do polar and cylindrical coordinates. Right. There's another coordinate system out there. It's slightly different than normal tangent. Turns out it ends up being the same as normal tangent for circles, though. So